Welcome. Let's look at velocity and other rates of change. Velocity is a rate of change, but other things can change as well. And here we're going to look at the area of a circle whose radius is changing. Right? And this radius is measured in inches. Right? And it's the unit of time. And by the way, this is in your notes. Time is going to be equal to seconds. That's going to be our unit of measure for time. All right, so the equation for the area of a circle is pi r squared. Right? And that's our unit of measure, of course, is going to be inches. The derivative, and actually let's make that a of t, because it's going to be a function of time, because you change over time. Right? So a prime of t, the derivative, we'll just take the derivative for the equation for area. So that's going to be 2 pi r, and our units of measure now will be inches per second. Right, so let's find a of 4, and then let's talk about what that means. Right? So a of 4 would be equal to pi times 4 squared. We're just evaluating a of t. Right? And that would be 16 pi, and our units would be inches. And what is that? That's the area of a circle. Is 16 pi inches when the radius equals 4 inches. Now let's evaluate the derivative when t equals 4. Right, so that's going to be equal to 2 pi times 4, which would be 8 pi inches per second. Excuse me, inches, inches per second. Right? And, no, actually, I'm sorry, inches squared per second, because this is area. Inches squared per second. Right? And then, what does that mean? That means the area of a circle, because if we're talking about the area, right, it has to be inches per second squared. Or inches squared per second. The area of a circle is increasing at a rate of 8 pi inches squared per second. Right? So our derivative is always describing a rate of change. Right? So when we're evaluating a derivative, we are finding a rate of change given a position point, a moment in time. Right? And if you're given a rate of change, always know that that is the derivative. Right? The average rate of change from 3 to 5. Right? So now we're looking at we're going to be evaluating we're going to be finding the slope of the secant line, right? So what we're finding here, when we're looking at the average rate of change, we're looking at a of 5 minus a of 3 divided by 5 minus 3. All right? That is going to be our average rate of change. And it approximates, let's actually add that in, the average rate of change approximates the instantaneous. Oh, I don't think I can fit the word instantaneous in. We've lost some of our words. I'll just abbreviate. there we go, instantaneous rate of change. All right, because we know the slope of the secant line approximates the slope of the tangent line. Which is the derivative. All right, so now we'll just evaluate. All right, so A of 5, all right, so that's going to be 25 pi, right? I think you're okay if we just do that in our heads. We're just plugging into pi r squared. Minus, right, evaluating pi times 3 squared, right, that's just going to be 9 pi divided by 2. So that's going to be 16 pi divided by 2 is 8 pi, and that is inches squared per second. Now that's kind of interesting. So notice here that these just happen to be equal to one another. Rather interesting, right? Perhaps we have maybe a constant rate of change. And so if we're looking at, if our derivative is a linear function, and we have r to the first power, right? So when we have a constant rate of change, the slope of the secant line is going to equal, right, the slope of the tangent line. Let's add that in there. So constant rate of change let's see if we put it in. Slope secant equals slope tangent. Let me move that up just a tad to make sure you can see it. Oh, yeah. Oh, that goes up there. There we go. All right. So now I guess we'll go over to the graphical one. The temperature of a kiln, Y equals H of T. All right, so this is, if you will, this is here, it would be the kind of like a position function, right? But our instead of looking at a position in space, right? We're looking at temperature, right? So this here is our equation, right? It is not a derivative, right? The derivative would look at the rate of change in the temperature, right? This is just what the temperature is, right, over time, right? So it's kind of akin to a position, except it's really not position, it's temperature. All right, so now we want to find h prime of 2, h prime of 4, and h prime of 8. So how do we find the derivative if we're given an equation, right? We're going to find slope of the secant line. Actually, kind of slope of the yeah, I guess we'll call it the secant line. But we're trying to find it at a moment in time. So let's just put slope equals derivative. That's probably the best way to write that. So essentially, we're looking for the slope, but we're trying to find it at a moment in time. Yes, we have to approximate, right? So all of these are going to be approximations, right? Because we don't have an equation here, right? We have h of t. And so that's just the name of a function, right? It's not giving us an equation that we could actually take the derivative of. So we're using the graph to find the slope at various points. All right, so now h prime of 2. All right, so we're finding the slope, if I can get it on the equation, the slope of that line. All right, so now we have to kind of approximate that a little bit. All right, so this is going up by 300. All right, so each one of these is 300. So it doesn't seem like it could be about 100. Maybe it's just a tad less, right? It is positive, right? So the rate of temperature is increasing at that point. It looks like to be about 75. And that would be 75 degrees Celsius. And then we're looking at a rate of change, so we need the unit of time per hour. If I can squeeze that in there. Right? Now, what if you thought it was a little bit more? What if you thought it was 80, or 90? Right? Well, with a range of 300 per line there, that's not a bad approximation. It just seems a little bit less steep than that to me, than 100. So I'm going with 75 degrees. Right? And I have to approximate that. Now, the next one is pretty easy to approximate, right? Because it is h prime of 4. Well, look what's happening at 4. We have a horizontal secant line. Our temperature is leveled off, and it stays the same for a while until it starts to cool down. All right, so I think we can all agree that's 0 degrees per Celsius per hour. There's no approximating there. All right, so now finally we have h prime of 8. All right, so here 8, looking right here. Well, I know one thing. That's definitely negative, so we know it's going to be a negative, and it is not as steep. Let me just draw that again. That is not as steep as that black line, h prime of 2, right? So it's going to be negative, and the rate of change is going to be less than 75. It looks to be about half as much, maybe even a little less. Let's call that negative 30 degrees Celsius per hour. Right? So when we're doing these and we're trying to figure out the slope given an equation, there's going to be a little bit of approximation. Right? You should be, approximately accurate. Are you going to be exactly accurate? Not unless you have a very precise graph, right, where we can see very small incremental changes. On a graph where our y values are going up by 300, I think we've done the best we can. All right, so now, average rate of change from 0 to 3. All right, now that one we can be far more precise because all we have to do is identify the temperature at 0 hours and at 3 hours, right? And then we're just using the slope formula. Right? So at 0, right, well, that's just about 0. It's a tad more than 0. So that's 300. And so halfway here, that would be 150. Well, it's not even 50, right? Maybe that's 25, right? So let's call this here 0.25. All right, so maybe we do have to approximate, just because we had to approximate that point. But once we've decided on our points, we can get an exact answer. And then 3, I feel really confident that is, actually, let me just take a quick look again. Let's just make sure that that's not going all the way to 0. No, it's not at 0 degrees. So it's probably room temperature. But let's call it 25. Actually, if it's room temperature, it's going to be 37 degrees. And that would really seem reasonable. So actually, I'm going to go, since it's Celsius, room temperature is 37 degrees. So it might make sense that the kiln would be at room temperature, right, before you start heating it up. Right? It wouldn't be at 0 degrees unless we put it in the freezer. Right? So let's call that room temperature. And then right here, I think it's quite clear what that value is. That would be 3,900. So our average rate of change, and I don't think anyone would argue that we decided that was room temperature, that seemed reasonable, right? And based on the graph, that's a good estimate. All right, so our average rate of change is going to be 900 minus 37 divided by 3 minus 0. And I am going to use a calculator. And of course I grabbed the calculator whose batteries are dead. So 900 minus 37 divided by 3 is 287.6666666. So 287.6667 degrees Celsius per hour, right? Expect positive as a positive slope, and that is our average rate of change from 0 to 3 hours. Finally, let's do the last problem on this page. All right, so we have calculators produced in hundreds and is our x value, and our profit is our y value. And of course, the profit is going to depend on the calculators, right? So, on the number of calculators we produce, right? We don't produce any calculators, we're not going to make any profit. All right, so we want to approximate p prime of 9, all right? And that is going to be, so we want to approximate the derivative. That is what approximates the derivative, of course. It's the slope of the secant line, right? So the slope of the secant line approximates the slope of the tangent line, right? So that is, and we want to be as close as possible. All right. So now, if we look here at our graph, where does 9 lie? Of course, it lies right between 8 and 10. So if we want to approximate the derivative when x equals 900 calculators, so we know 9 is 900, when x equals 900 calculators, we're going to find the average rate of change, right, at from 8 to 10 seconds, right? So that's going to be p of 10 minus p of 8 divided by 10 minus 8, which is 13.2 minus 11 divided by 10 minus 8, and that is going to give us, so 13.2 minus 11 is going to be 2.2. That's pretty easy. I need to calculate for that. And we don't need to calculate for anything here. Actually, I probably should keep this as approximately. I mean, it's exactly the slope of the secant line, but it's approximately the derivative. So 1.1, and we want to make sure we have the correct units here. So it's thousands of dollars per hundreds of calculators. All right, so I'll write it down here. P, because I don't think I can fit that units of measurement in. So P prime of 9 is approximately 1.1 thousands of dollars we'll put that dollar symbol in there, per hundreds of calculators, and I'll abbreviate. And the shadow of my podium is blocking, so I'm hoping that that's legible. I'll just have to hope, because I can't move my podium yet. All right, and so remember, if you're given a table, or if you're given any data, and you want to approximate the derivative, just find the slope of the secant line as close to the derivative as you can, right? We wouldn't take 6 and 12, right? We want to be close to 9. We would take 8 and 10, all right? And these problems are done, all right? Let's look at the next page, which again is dealing with graphs. There we go. Position, speed, and acceleration, and velocity. Mr. Bean is playing catch with his best friend, himself. He throws a tennis ball straight up into the air. The height of the ball is modeled by S of t equals negative 4.9 t squared plus 18t plus 2, where t is time in seconds and s is height of the ball from ground in meters. Now you might be wondering why the negative 4.9. And on one of our problems in the last Nearpod, I kind of forgot that negative 16 is for feet and negative 4.9 is for meters. Right? So we do have an error in one of the problems because I forgot it was in meters, not feet, and I forgot to change the coefficient. The V naught wouldn't change, the S naught wouldn't change, but that coefficient changes for meters. All right, so this is gravity when we're dealing with feet and when we're dealing with meters. All right. So so we've gone through the problem. Here we have the position equation. Notice, of course, it's going to be a parabola. When you throw something in the air and you drop something, the motion is a parabola. Right? You think it's straight in the air, but it's not. So here we have our position. Let's look at direction here. So right here, our object stops. And how do we know? The position's not changing, right? That moment in time, the position does not change. Here we're moving in a positive direction. Here, so in other words, up. Here we're moving in a negative direction. In other words, down. Right? But you have to stop for a moment before you can move down. Right? So here we have our ball moving up, stopping for a second, and moving down. Right? And as a function of time. Right? Right? So now let's compare that with the velocity. So notice where we have a horizontal tangent on the position function, we have an x-intercept on velocity. Right? So right here, the object is stopped. The ball is stopped. Right? And we know that because v of t equals 0. Where the velocity curve is above the x-axis, we are moving in a positive direction. And that's because v of t is greater than 0. Where the velocity curve is below the x-axis, we are moving in a negative direction. I don't think I need an A in there. And that's because v of t is less than 0, right? Above the x-axis, positive, below x-axis, negative. There we go. Let's compare, now if we were looking at speed as opposed to velocity, right, speed would just, this section here, that would just be reflected up, right? That'd just be reflected up. All right, so now let's look at acceleration. All right, so with acceleration, that is the rate of change in velocity. Notice that the, actually let me just mark that this here, let's get rid of this. So this, oh, I forgot. If I erase anything, because purple is a special color, if I erase anything, purple goes away. So this is speed. which we know equals the absolute value of velocity. Now, notice that velocity is a constant, changes a constant rate. We can see that because it is a linear function. All right, so what does that mean for acceleration? Right? Acceleration is constant. Since v of t equals a constant rate of change. So velocity is not always the same, right? Each of those y values is a different velocity, but because it's changing at a constant rate, it's a linear function, acceleration is going to be a constant value. All right, and so here, let's actually find the velocity, let's find we have the position equation, right? And by the way, if we're looking at this, that that's not good. The 18, the initial velocity, so the v naught is 18 feet per second. It is a constant rate. The initial height is 2 feet, based off of our equation there. If we take the derivative, so the equation for velocity is going to be negative 9.8 t plus 18. And if we take the derivative for acceleration, a of t is going to be a constant negative 9.8. Okay? And of course, our position function is in meters. Our velocity function is in meters per second. And the acceleration is meters per second squared. All right, and here, notice we're below the x-axis, right? We have a slope of velocity is negative, which of course means that how's velocity going to be negative unless the direction, oh, excuse me, no direction, sorry. Ignore that. Sorry, velocity is not always negative. The slope is negative, right? So slope of velocity here is negative. How do we know that? A of t is less than 0. Right? And so if we were just looking at a velocity, we would know. So let's just say we didn't have an equation at all. If we were looking at the graph of velocity, notice it has a negative slope, right? So if it has a negative slope, we know that the equation for acceleration is going to be below the x-axis. And we can easily find the equation even from the graph because we could find the slope of that, of the velocity curve here, which is just a linear function. All right, and I think we've talked all we can about these particular graphs. So thanks for watching, and bye for now.